All right. I hope everyone is doing good. My name is Jesse, and I'll be your MC for today. We have a wonderful speaker with us today by the name of Xiao. Xiao is a machine learning engineer from Pinterest. She currently works on building shopping recommendation systems and improving the mid-funnel shopping experience on shopping surfaces at Pinterest. Before Sai joined Pinterest in 2018, she's also worked in data science in a few companies such as Liberty Mutual, eBay, and Apple. She received her PhD in statistics from University of California, Santa Cruz. Sai's talk today is titled Shopping Recommendations at Pinterest. As a quick reminder to the audience, please take some time to fill in the session polls. And if you have any questions during the talk, please post them in the chat and Sai will be able to answer them at the end. So without further ado, Sai, please take it away.
Hi, thank you for introduction, Jesse. Okay, I'll start my talk. Hi, I'm Sai from Pinterest. I'm currently working in shopping discovery team. I'm based in Palo Alto, California. So I've joined Pinterest for 3 years. Today, I'm going to introduce you the shopping recommendations from Pinterest. All right. Okay, Pinterest is the visual discovery engine. Our mission is to bring everyone the inspiration to create a life they love. So on Pinterest, the people share billions of pictures and explore for new ideas such as travel, cookie, home improvement, fashion, and beauty. So we use term pin to refer to those images, videos, and the stories shown in Pinterest. And the pinners can collect the pins and organize them into boards. So there are many ways that you can play with Pinterest app. For example, when you open your Pinterest app and before you do anything, you will see we already prepare you pins that you may be interested in. So those pins are generated by our recommendation system based on your interest and behaviors. And when you browse them and take some actions on them, you will get more and more information and maybe some new ideas, and we will update the information about your interest. Besides that, you can also do some keyword search or visual search, and we will retrieve and recommend relevant pins to satisfy your query. When you click into the pin, we will show you more similar ideas to get you inspired. We have a lot of experience in recommending organic pins in these services, and now we are taking what we learned from this service to develop shopping recommendations and help you to shop in Pinterest. We have 478 million people from all around the world come to Pinterest each month. So we already collected 300 billion pins saved in Pinterest, and we have 6 billion boards created. From the boards and pins user collected, we found a lot of shopping intent in Pinterest. So shopping has a great potential in Pinterest. So from the public survey, we know that 83 of the pinners have made a purchase based on the content they saw from the brands on Pinterest. And shopping is also growing very fast in Pinterest. We observe more shopping browsing, so there is 215% growth in the number of pinners engaging with shopping services on Pinterest in the past year. There is also much more discovery about shopping. So we find out product searches grow by 20 times in the last year. I'm very excited to say shopping is live in the US and UK, and just starting this month, June 7th, we launched the expansion of our shopping features for pinners and merchants to Australia, Canada, France, and Germany. So shopping is officially global in Pinterest. So we know that people like to purchase in Pinterest or do some shopping discovery. So we provide different entry points for the pinners to get to the shopping services. Here I list a few examples. So the close-up shop. When user tap into our non-product pin, so the object detector will identify the products in the home decor and fashion tag categories. So once you tap into the tag, you will find product recommendations looking very similarly to the object you tapped. In search, for the high shopping intent search queries, we offer shop tab feature. We show you the product pins from different merchants available in your geographical locations. So those products are organized by different recommenders. For example, shop by brands, shop by category, or shop by styles. We also spend a lot of time to developing the product page in Pinterest. So once you click into the product pin, we show you accurate and complete product metadata for those products. So those products actually covers tens of thousands of merchants. Actually covers all major merchants such as Wayfair, Home Decor, and etc. And you can see the metadata looks like title, description, price, shipping information, and ratings. And after those information, we will offer multiple recommenders. For example, Shop Similar will provide you the most relevant pins, like substitutions, and visually similar pins. We also develop other recommenders, such as more products from this merchant and more products from the most popular pins from the same category. Besides that, we also have some recommenders based on collaborative filter to learn from the co-occurrence of two products to recommend you people view, or people also bought, something like that. Okay, so I want to share some challenges that we identify of building recommender systems. First, the massive scale. We have hundreds of million product pins in the catalog, and we need to serve those recommendations for hundreds of millions of pinners. So there's a lot of scalability problem. Second, in today's recommender system, the future data types become more richer. So it contains user profiling features, text features, images, videos, and graph. Third, the recommender will need to optimize engagement, maybe different types of engagement. And at the same time, we need to balance other factors, for example, relevance, diversities, and also inclusiveness, like skin tone. Moreover, not a single recommender will fit all the shoppers' intent. We need to build multiple of them to accommodate people's different intent. And one problem is how to develop new recommenders fast and quickly onboard them. The last one, once we have multiple recommenders, we want to optimize the whole page to decide which one we want to show and which one, like where to want to display and in which UI. Okay, so this is the overview of the backend system. So first, we have built a huge product catalog, which includes both merchant-ingested product pins and user-provided pins to power all the shopping use cases on Pinterest. So this is definitely the backbone of all the shopping features. And then on top of that, the recommenders will consume the product catalog to retrieve and provide different types of recommenders. For example, related products, query-based recommenders, and collaborative filter-based recommenders. And then on top of that, we have the shopping page optimization mechanism to select the recommenders to show and decide which one to show on the top. So this will significantly improve the user's shopping experience and also reduce the cost of showing too many recommenders for the user. So this whole stack of techniques will support multiple shopping features, shopping services such as product detail page, shop tab on search, and shop tab on board. Okay, so next I will focus on introducing the technical details about how we build similar product recommendations. We mainly focus on introducing the recommendations in the context of product to product recommendations. So this system will taking the query product and the user as the input, and then the output will be a set of products which similar to your query product, but also match the user's preference. So the whole system actually can break into two parts. One is the candidate generator, another one is ranking. So the candidate generator takes in the query products and sometimes the user as the input. It will retrieve sufficient but most similar candidates from the catalog. So it's basically to narrow the hundreds of millions of catalog into just 1,000, approximately 1,000 candidates. And then in the ranking stage, it will apply some machine learning algorithms to rank the candidates and then select the top K candidates. So we also apply some relevance guardrails such as gender match or broad category match trust and safety check to trim out some of the irrelevant pins before we serve those pins to the users. So let's deep dive a little bit to the candidate generator. We built candidate generator through several sources. For example, MapBoost, we utilize the historical engagement data to generate the source. We also have pinboard graph candidates, and one of them works pretty well is the engagement embedding-based candidate generator, which leverages the deep learning model. So this is the embedding-based candidate generator diagram. So actually there's two parts. One is how we generate the product embedding representations. We use DNN model to generate product embeddings for the whole catalog, and we save them into the embedding store via some offline workflow. And then we also have the retrieval model. In the online serving phase, we look up the embedding for the incoming query for the, from the embedding store. And then we do a nearest neighbor lookup from the whole embedding store to find out the top K candidates pins. So let's see how Pinterest builds our unique embedding for billions of pins and millions of products in a scalable way. Yeah, one thing we found very unique in Pinterest is that we have lots of graph data. As you know that people will save some pins into the boards. We assume that those pins in the same board actually share some semantic meanings. And how do we use this graph data as input features? We think pinboard graph is a very good tool that we should use. So it's basically a visual bookmarks to online content into boards. We model the Pinterest environment as our biparty graph, consisting of nodes in two disjoint sets, pins and boards. So we want to use this graph in our model, and the benefit of this is that we can borrow the information from the nearby nodes in the pinboard graph. So the resulting embedding of this node will become more accurate and more robust. So for example, a bed rail, it might look like a garden fence, but the gates and beds are really adjacent in the graph. So our model will rely on this graph information and to provide some context. And then it will allow us to disambiguate the pins that are visually similar but semantically different. So we built a graph convolutional network algorithm, and the model is called PinSage or GraphSage. So first, it has a context features. So for each query pin, it's associated with multiple data types, providing certain information like image or a set of contextual annotations like title, description. So we incorporate those in visual embeddings and textual embeddings, and so we can get information from both image and the text. We also have graph features, which is to utilize the pinboard graph we just mentioned in the last slide, and we do the localized convolution operation. We apply some aggregation algorithms and provides a vector representation of its local neighborhood. And then we concatenate this aggregated neighborhood vector with the contextual, with the query pins contextual features together and transform the concatenated vector through some dense neural network layer. We have millions of engagement data as labels. So for example, click. If you see this pin and you click that pin, so we have the click data, we have the save data. So this can be used as labels. So the model is learned from our standard triplet loss. So one thing that we found this graphical convolution neural network model is that we need to scale both the training and the inference of this model with billions of nodes in the graph and maybe tens of billions of edges. We need to do it in a scalable way. And this graph is also growing over time. So the traditional graphical convolutional neural network recommenders might require operating on the full graph, but it is not infeasible for us. So we did some key innovations to make it more efficient. one thing we did is that we do some localized convolution by sampling the neighborhood around the node and dynamically constructing our computation graph. Also, we use random walk to select a set of neighbors to convolve over. And we're just selecting the neighbors with the highest visiting counts. And we also represent the nodes with contextual features for inductive inference instead of using the ID. We have more details in the KDD paper, so feel free to check it out. Okay, so now we talk about how the embedding is generated. I want to talk a little bit about how the embedding is served. So we built the efficient approximate nearest neighbor search by leveraging our backend search engine as the distributed serving platform for the nearest neighbor search. So we retrieve the candidates by using the state-of-art AAM methods. Currently is HNSW algorithms. So I list the paper here. And then we built the AAM batch indexing via Hadoop for the static index, and also have the near real-time indexing for the flash pins. Okay, so embedding-based candidates is one of our candidate source, but we have multiple candidate source. How do we index them and retrieve them efficiently? So here, this is the diagram. And we have another requirement is that we need to search candidates by some constraints. For example, we only want to retrieve the candidates below, for example, $10. So one of the important components in this indexing framework is attribute. So the attribute are properties of each search document, and each document in the product corpus will have embedding graph-stage embedding associated with it, and other properties such as price, merchant, category, and style. So at a high level, the framework manages the conversion of a corpus into a search document, and then we merge this bunch of attributes together, used for filtering as the serving time. So the benefit of it is that we can include multiple candidates into one index, and also these attributes can be shareable by these candidates. So this will allow us to define the attributes once for all the candidate sources and simplify the query composition at serving time. This already increased the engineering velocity when we build different kinds of candidate generator and adding more attributes to shareable to them. As I said, besides embedding-based candidates, we also have engagement-based candidates. So this is basically to collecting the historical user engagement data in the past year. So for each query pin, we have a list of historical engaged pins as candidates. How to incorporate this into the previous index? In order to do that, we convert the candidate. We converted the original list to a candidate corresponding to a list of query pins, and then we put it as our attribute in the attribute for the search documents to merge. And then we can utilize its index to build the inverted index forward index. And we can also share the attributes to do the query against our engagement-based candidates. Okay, so this is a very flexible indexing framework that helps us to onboard some of our new recommenders in a fast way. For example, by configuring different attributes in the query composer, we can build different types of recommenders. Given that in our corpus, we have already contained all required metadata, for example, price, category, style, and domains, brands. So if we specify the brand restrict in the query, so the retrieved candidates will only be the candidates from this brand. So we can build a candidate, we can build a recommender, so-called more from this brand. Similarly, if we specify some price limit in the query, then all the candidates retrieved will be below this price limit. Then we can build a recommender, so-called items under certain bucks. So this will give us a lot of flexibility to build recommenders very fast. Okay, let's jump into the ranking part. The ranker basically to build a machine learning model to predict the probability of engagement given the query ping and the user. So here engagement is very vague because in Pinterest we have different type of engagement. For example, save, close up, clicks, long clicks, and conversion. And we need to build a personalized ranker. So how do we handle different types of engagement in a ranker? So we utilize a multi-head DNN model. And we have different types of features like graph stage embedding, user embedding, test match, and the shopping signals. We put them together so we can build a personalized ranker. And then we use AutoML to construct our DNN model by grouping all these features and cross the features in the fully connected layers. So Pinterest AutoML is our self-contained deep learning framework that will power feature injection, feature transformation, model training, and model serving. And this output of this DNN model will output four output heads, and each corresponding to one engagement type. And the four output heads can borrow information from each other by sharing the previous layers, and will also reduce the overfitting problem. After that, we will apply some simple calibration step because we do some negative downsampling in the training data. After the calibration step, the scores of the four heads will be interpreted as the probabilities of each engagement type. In the last step, we will combine the predicted score by the utility function to generate a single engagement score to rank the candidates. So one probability per engagement type actually will give us a lot of flexibility in the ranking of the candidates. We started very simple by just using a linear combination of the scores as the utility function. And this actually one motivation is that we want to decouple the business value from the engagement prediction. So we can adjust the weight in the utility function to accommodate some business requirement, for example, to emphasize some of the engagement type without retraining the predictive model. All right, here is to summarize. To summarize, we have the state-of-art recommendation techniques to build our recommendation systems. So for example, engagement-based candidates and the multi-head DNN ranker to help us to improve the engagement metrics significantly. And ultimately, we want to build a unique shopping experience at Pinterest to help people get inspirations, ideas, and also can purchase in Pinterest. Okay, thank you for listening to this talk. And I'm very glad to say that we have a brand new Toronto office and we are hiring. The work in Toronto office primarily focus on shopping. And you will see a lot of machine learning openings in shopping discovery, shopping content, and the shopping product team. So if you are interested in e-commerce, shopping recommendations, and AI techniques, please don't hesitate to check out our career website or just scan this code and to get more information. Thank you. Thank you very much.
All right. Thank you very much, Sai. This was a great talk. I learned quite a lot about Pinterest and the amazing things you guys are doing. Do we have any questions from the audience? I don't see any questions in the chat. We have a couple of minutes left, so please go ahead and ask some questions if you have any. If not, thank you very much, Sai, and thank you very much to everybody in the audience. I, for one, will be applying to Pinterest, so thank you very much for letting me know about this opportunity. And wish you everybody a good rest of your time and enjoy your day. Thank you, Sai.
Okay, see you.
Alrighty, take care, everybody.
Bye.